There you go.
Can you see me?
Yes. All right. Kia ora.
Kia ora, everyone. Kia ora, Aotearoa, and the rest of the world.
Kia ora, everyone.
Kia ora.
So here we are again for another one of those mighty Facebook Lives. So I'm your host, Adrian. This is Luca here, and we have Manon à la technique. I hope that you guys can hear us, and that the video is working fine.
Same again, if you can let us know if you can hear us, if you can see our screen, if you can see the webcam, all of those things, just put a comment so we know that we are all
Drop
good
us
to go.
Comment or like or a question. You can start your questions ready.
All right.
All right. Yes. We start having some people. Hello,
Katie.
everyone.
Hello,
Hi,
Katie.
Colleen. Hi, Katie. Hi, Jem. Hello, everyone. So, well, what's going to happen tonight? I will start with giving a little introduction on the sky tonight, what we can see tonight in the sky, if you have a clear enough sky, in the southern hemisphere, of course. Then I'll be answering any questions you guys may want to ask us on the comments. So please do ask us questions. We'll have plenty of time to answer any of your questions. And then a cool thing tonight as well. We're gonna be having a chat toward the end of this live with Dr. Ryan Readen. So Dr. Ryan Readen is an astrophysicist from University of Canterbury's Research School of Physics and Chemical Sciences. He's a guy that has one of the coolest job titles. He's specializing in the most explosive events in the universe that are caused by exploding stars, colliding stars, and angry black holes. So if you have any question about the death of stars, so we'll be talking about the death of stars, massive stars, non-massive stars, how do stars die? And one big word that you may have heard about before, and that's linked to this topic, is supernovae as well. So we're going to be speaking about this with Dr. Ryan Readen towards the end of this live. You can prepare all of your questions, and just had the ISS, Rod just had the ISS pass over Hope. So that's cool. That's cool. That's always a cool sight to see the ISS. That's the good time to see it. You see the ISS shortly after sunset or shortly before sunrise, because this is when the ISS still has sunlight to reflect back to us. In the middle of the night, if the ISS passes over your head, the ISS does not catch any sunlight, so it's not really visible. It's important to note that whenever you see the ISS or any other satellite, you're not seeing any light produced by the ISS. You're not seeing the light out of the window. You are just seeing the reflection of the sun on the huge solar panels of the ISS. But that's always a very cool sight. All right, well, let's get started then. So I'm going to start with I like to start now with the same way as every planetarium show starts. The sky tonight. What are we gonna see tonight? So what you have on the screen right now is a software called Stellarium, and that is a very powerful, a very great planetarium software that is free, so you can download it, free and open source. You can download it on any platform and play around with it. And I'm showing you here a real-time image of what is the sky right now. To be fully honest, the sky right now here in Berg's Pass is not like this at all. There are a lot more clouds, so we cannot see anything with our own eyes, but thankfully computers can show us what we cannot see otherwise. So let's start by having a quick look. I like to start these sky tonight topics with the position of the best constellation of the southern sky, the mighty Mahutoka, the Southern Cross, right here. So the Southern Cross right now is reasonably high in the sky, pointing towards the left, pointing towards the east to be more precise, and it will slowly get lower and lower as time goes. And in case you are not familiar with how to find the Southern Cross, and if you have a bright enough sky, clear enough sky tonight, look out for the pointer stars that you can see here, Regal Centaurus and Hadar, or Alpha Centauri and Beta Centauri. So those two stars are called the pointers because they point to the tip of our mighty Mahutoka, or mighty Southern Cross. A very important constellation because it is the best tool we have for celestial navigation. What else do we have? Now, If you turn your gaze to the east, and you'll have to look a little bit up, and you will see the brightest thing that you can see that is nearly straight east at the moment is the mighty planet Jupiter. So Jupiter is already quite high in the sky at the beginning of the night these days, and it is the brightest object in the sky, unless you had the chance, like one of our viewers, to see the ISS, which can be even brighter than Jupiter, but it's moving. Jupiter is not moving against the background, or not very fast, so you can see it. You can see it pretty easily. You can identify it pretty easily. And if you have bionic eyes, you may be able to spot those 4 dots around the 4 moons of Jupiter. Interesting to note. So I'm kidding, by the way. No one can see the moons of Jupiter with their eyes. But that is not because they're too close to the planet. That is because Jupiter is too bright and washes away those four Galilean moons. If you remove Jupiter, the Galilean moons would still be definitely visible to the naked eye. They are pretty big objects. Now, let's do a bit of star hopping. You start from Jupiter, and you go top left, and you should see another brightish dot, a lot less bright than Jupiter, but still very easily seen from any place, as long as you have clear skies. Light pollution does not affect, well, does affect everything, but even with a light polluted sky, you can see Saturn pretty easily. And Saturn will be right up here, top left from Jupiter, if I zoom out a little bit so you can see this in its context. And now, I don't want to do any astrology, but I can tell you that Saturn and Jupiter are currently in Capricornus. Right, that big triangle here, I don't know if you can see this triangle. So this big triangle here is the constellation Capricornus, which is supposed to look like a creature that is half goat, half mermaid. Good luck with that. And I just see a bunch of stars here, but plenty of people with a very good imagination saw different shapes in the stars a long time ago. Just to show you what it's supposed to look like, so that part here is the Capricornus constellation. Now, if you have a lot of imagination, that's what you see. Half goat, half fish. I am not too sure where that one came from, but there you go. This is the Capricornus constellation. And Jupiter, as you can see, is actually very close. It is halfway in between Capricornus and Aquarius here. This is the constellation Aquarius. Another one of those zodiac constellations. Important to note that every time you see an object of the solar system, a planet, the moon, or the sun, it will always be inside of one of those zodiac constellations. Another thing that is quite often misunderstood about constellations. Constellations are not drawings in the sky. This is how we know them. But this is not what they are to astronomers. To astronomers, a constellation is a portion of the sky. So the sky is actually divided like a map, like countries in a map, divided in 88 different constellations. And Jupiter is officially in one of those 2 constellations. I am sorry, I am not quite sure right now officially in what constellation. There you go, Capricornus. So Jupiter is still within the constellation Capricornus, but it is very close to the limits with the Aquarius constellation. Let's remove those drawings, because to my opinion, they don't make any sense. And let's continue and see what we have. So take Jupiter, take Saturn, and continue all the way up. Draw that line and continue up, and you will end up there. That is probably straight above your head. That is the center of the Milky Way galaxy. Unless you are under a very dark and polluted sky, you will not see the band of the Milky Way that bright, but this here is the center of our Milky Way galaxy. That is, there's 2 important zodiac constellations in here. We have the magnificent Scorpius there, and we have Sagittarius right here. So Scorpius looks like a scorpion. Can you see that beautiful tail and a tiny stinger here? It is the best constellation in the entire night sky. And Antares here, this is the Western name. The Tereo name for Antares is very dear to us. Antares is called Rehua in Tereo. And Rehua is the name that we gave to our building to the Dark Sky Project base in Takapo. Because Rehua is linked, is an important object, an important star and an important god in the Maori star lore. Rehua is one of the kids of the two main creator gods, and Rehua is responsible for bringing knowledge on the people of the earth. And that is what we do, bring knowledge. So this is why we called our building Rehua. And then right here, let me just display those drawings here. So this here is the Scorpius, and right here we have Sagittarius. So Sagittarius is a bit hard to make out because he is half man, half horse, shooting an arrow. Let me show you what this looks like. It's upside down, but there you go. That's your half man. He's about to shoot an arrow. So these type of stars, these line of stars here is the arrow that is about to be shot by the Sagittarius and towards the Scorpius. And then for the half horse, you really have to use your imagination a lot when you look up at the sky, because it is pretty hard to make out really. But if you struggle to see this here, I have another little thing that may make it a bit easier. We sometimes refer to this constellation as the Teapot, because it does look like a teapot. Even if I remove these, it does look like a teapot. So here you have the lid of your teapot. That is your handle. That is the bottom of your teapot. And that is the spout here. So if you ever hear about the constellation of the Teapot, it is actually very likely the constellation Sagittarius, but a teapot makes a lot more sense. I believe that by the time they invented the names of those constellations, they did not have many teapots around. If they did, that would very likely be the constellation of the Teapot, but it is now the Sagittarius constellation. All right, Francisco telling us that, yeah, they used Stellarium when they were doing their 4th year of astronomy degree. All right, that's great. You see, Stellarium is a software that is awesome, not because it looks good, but because it is also very useful to understand things and to explain things. So I am happy to hear that, Francisco, and I'm not surprised because many astronomy students do use Stellarium as well. We use Stellarium as guides. We train a lot using Stellarium because, as you can see, when you don't have a sky to look at, you always have Stellarium to look at, and it is quite powerful. You may have seen a little thing here. I'm just going to re-show this Sagittarius constellation. So that part here is actually you may think that it's part of the constellation, but it's not. This is called Corona Australis. So it is very recognizable. If you have a dark sky, you can see that kind of curve of stars. It is quite recognizable in the sky. And yeah, it is not part officially of the Sagittarius constellation. It's a little bit a little add-on to the constellation. Let's put it that way. We have down here in the north Altair, right next to the bend of the Milky Way here, and on the other side of the Milky Way, a star that is, to be honest, not really a southern sky star, but we get to see sometimes as well, Vega. So Vega is really close, as you can see, to the north. So it is a very far northern star, so we don't see a lot of it from here in the southern hemisphere. But those two stars, Altair and Vega, are involved in a very important celebration about astronomy in Japan. That is the Tanabata Festival. I'm not gonna try and give you the names of those characters in the Japanese culture because I don't remember them, but Altair and Vega are two lovers that are unfortunately separated by the Milky Way. And during the Tanabata celebration, which happened around last month, I don't remember the exact date, but this is the celebration during which we consider those two stars can join each other and experience their love once a year, but otherwise they are separated by the Milky Way. Plenty of beautiful stories up there in the sky. But the most beautiful stories of all are not those ones, to my opinion. I like the stories of the physical stories, what those objects really are. So we're gonna get there. We're gonna talk a lot about those physical stories. All right. Now, I've introduced a little bit of what the sky looks like tonight. I'm gonna talk a little bit more about this eventually later on. And of course, if you have questions, please do ask your questions. I will be very happy to answer any of these. And in the meantime, before we start introducing this talk we'll have with Dr. Ryan Readen, we've had a request the other day about the cycles in the sky. So how the sky moves And what kind of cycle can we find? So there is a daily cycle, a yearly cycle, a monthly cycle. Let's have a look at all of this and try to understand a little bit better. This is something that is actually quite important to understand very basics of astronomy, and for example, to be convinced that the Earth is round, because it really is round. And if you understand those cycles, if you understand how the sky turns, etc., it is a lot more obvious. And let's try and do this. I'll start looking at the south. And the first cycle is the very obvious one that you guys all know about. It is the alternance of day and night. So let's accelerate time and see how that works. So the sky seems to turn around a central point that is very easy to find thanks to the Southern Cross, because the Southern Cross is pointing towards that point. Somewhere up there is what we call the South Celestial Pole, the projection of the spin axis of the Earth up into the sky. So I'm accelerating time here quite a lot. It is now 1:30 a.m. It's 2 a.m. now, 2:30 a.m. So this is to give you an idea of how fast I'm going. One day, I know this might sound super basic, but getting definitions is pretty important. One day is the time it takes for the sun to come back in the same location in the sky from any given location on the Earth. And you may think that a day lasts 24 hours. Easy. Well, it's a little bit complicated than that. One solar day lasts 24 hours. And by the way, let me remove the atmosphere so we can see this. Oh, by the way, before that, can you see this beautiful landscape? That's what we see from the summit of Mont John. I have the beautiful Lake Teapot here, the megalopolis of Lake Teapot. This is the view you get from the Astro Cafe. Up on the summit of Mont John. Quite a beautiful 360 degrees view on the entire Mackenzie Basin. This telescope is the 16-inch telescope. It is the one that we use for our stargazing tours. All right, let's go back to the north. Sorry, to the south. There we go. So you may think that it takes exactly 24 hours for the Earth to turn exactly once around its axis. Well, no. It doesn't. It takes 23 hours, 56 minutes, and 4 seconds. However, your clocks, your days, your clocks are set on 24 hours. We don't have to account for those 4 minutes. So what is this exactly? And I'm going to try here to explain this concept, this difference between what we call a sidereal day that lasts 23 hours and 56 minutes, and a solar day that lasts 24 hours. Bear with me. That is not going to be easy. I'm going to try, but it's not such a super easy concept. I mean, it's a relatively straightforward concept, but explaining it's not going to be that easy. Let's try. And for that, I'm going to try and show you a little image that should make things a bit easier here. So I'm just going to go to my folder that I have been preparing for this live. And there you go. All right. So on the left here, you see the definition of a solar day. So imagine you are here on the Earth. A solar day is the time it will take for the Earth to complete one rotation in relation to the sun. That's important. The in relation to the sun is important. Because look at it from this software. All right. I'm showing you here, that is the Earth in the center. That is the orbit of the moon in green around the Earth, and in red it is the orbit of the Earth around the sun. So I have to zoom out a lot until I can see the sun down there, but there you go. That's how it works. So let's go back to the Earth. So one day, it's quite easy. It is how long it takes for the sun to rotate for the Earth to rotate until the sun is back on the same position in the sky. But then during this time, the Earth has also been moving a little bit on its orbit around the sun. It has been moving, so it takes exactly 365 days to complete that entire orbit. That's what we call a year. So during those, as the Earth was rotating, giving you this alternance day and night, well, the Earth has been moving a little bit on this orbit. Therefore, once the Earth has completed an entire turn, which takes 23 hours and 56 minutes exactly, well, the sun is still not there. The Earth has to move to spin an extra 4 minutes to get back to the sun. And this difference is what makes the sky seasonal. So let's go back to my little image here to try and explain that. once the Earth has rotated exactly 23 hours and 56 minutes, one full exact rotation, then what you see in front of you is just the star that was there 23 hours and 56 minutes ago. But the sun will be a little bit further. You will have to wait for the Earth to rotate an extra little 4 minutes to get back there. This means that every object in the sky, every star, every constellation, any object in the sky will rise 4 minutes earlier every single day. This is what makes the sky seasonal. So, for example, you want let's go back to our stellarium, and I'm gonna remove the atmosphere so that we can see the night sky even during the day. We can see the stars even during the day. Well, perfect. Enter us, Rehua, right here. So Rehua, we are. This is a bit of a random time. It's 10:43 in the morning in 2 days. So Rehua is right here, but in 4 minutes, and I'm going to show you that here by playing around with the times. There it is. If I move by 1 day, so the exact same time, see, it's still going to be 10:43. The 7th is going to be a bit higher. The 8th, a bit higher again, etc., etc. Every day, things rise 4 minutes earlier. After 10 days, things will have been rising 40 minutes earlier than 10 days before. And so this is what makes the sky seasonal. So this is why a few months ago, maybe 1.5 months ago, or maybe 2 months ago, we had the Galactic Bulge. This is what we're looking at here. The Galactic Bulge is what you see around the tail of Scorpius. The Galactic Bulge, the center of our galaxy, was rising right at the beginning of the night. As the sun set, you see the Galactic Bulge rising. That was the case a couple of months ago. But now, a lot of time has passed. Sorry, I'm moving the date here. A lot of time has passed. So at the same time of the night, now the rising bulge will be a lot higher in the sky. The galactic bulge will be a lot higher in the sky. So the season of the rising galactic bulge is actually not now. It's a few months back at the very early winter, at the beginning of winter. Now that we are getting to the end of winter, when the sun sets, well, the galactic bulge is already quite far above your head. All right. I'm sorry if that was a bit confusing. If you want me to re-explain things, or if you have specific questions to try and understand that better, please ask them in the comments. We'll be more than happy to answer this. That's what makes the sky seasonal. Now, that was for the sidereal day versus sun solar day. Now, just to evacuate the super obvious here, 1 year is the full rotation it takes around the sun, the time it takes for the Earth to achieve one full entire orbit around the sun. You can see that the solar system is a bit flat. All the planets are revolving around the sun on the same plane, and that plane is what we call the plane of the ecliptic. This is where you find the zodiac constellation. So if I use this software here, which by the way is called Celestia, and is once again a free open source software that you can install on any platform. If I display the constellations here, you will see behind that flat disk all the constellations that we are familiar with, the constellation of the zodiac. So that triangle here is Capricornus. We have here Aquarius. Here we have Sagittarius. Then we should have the magnificent Scorpius, which is not as magnificent in this software, but there you go. That is the Scorpius constellation. So there you go. This is where you find all the plane of the zodiac. We are in front of Virgo here, followed by Leo, followed by Cancer, Gemini. So here's Gemini, Taurus, with Matariki right down here. Aries, Pisces. There you go. Aquarius, and back to Capricorns. Isn't that pretty? I really strongly, if you have a little interest in astronomy and how the sky moves, etc., I strongly recommend to play around those softwares, Stellarium and Celestia, because they are free and they are quite awesome. You can figure out and understand a lot of things with those. All right, so now, as I mentioned, we're going to be speaking in a little while with Dr. Ryan Readen, and we're going to be speaking about quite a complex topic. we're gonna be speaking about the death of massive stars, and or the death of stars in general. Oh, before that, I see that we have a question here. Why? So, Bryce Curran, why do the planets align? All right, that's a good question. Why do planets align? So, first thing to realize. Let's go. Actually, I'm on the right software to answer that question here. Once you're in here, you see that since all the planets revolve on the same plane, well, we will always see them from that perspective. So from here on Earth, they will always be roughly in the same line across the sky. That is the line of the ecliptic. So we always see the planets somewhere on that line of the ecliptic. It turns out that the closer a planet is to the sun, the faster it's the shorter it takes to do one full rotation around the sun. So if I accelerate time here, you can see those little dots. Oh, let me center on the sun and follow the sun. There you go. So you can see those little dots. I hope you can see them here on the live. But those little dots here are our planets spinning, and they spin at different speeds. They're not random. They can be calculated thanks to the laws of Kepler, but they do move at apparently different speed relative to each other. As a result, when we see planets from the Earth, they will not be always at the same location. They will seem to be moving against the background of stars, and each planet moves at its own rhythm. So sometimes, and actually, there you go. Sometimes we have planets that will be aligning. So let's imagine that you are on the sun. I know that's a strange example, but I just have this example popping out right here. Right now, from the sun, you have those two planets here, which are Mercury and Venus, aligned. But that is just not a chance alignment, but just an effect of perspective, a matter of perspective. Well, the same thing will happen to other planets. So as I accelerate time, you have here what I believe is Jupiter and Saturn. Am I right? Yeah, Jupiter and Saturn. Oh, there you go. We're gonna get to an alignment between Jupiter and Saturn here. Look at those two, Jupiter and Saturn, and the Earth is this one here. So where is the Earth on that image right here? The Earth is here. So the Earth is right here. In this configuration here, you see from the Earth, you will see Jupiter and Saturn very close to each other. That is an alignment. That is why planets align. This is a conjunction. It's important to note that when two planets align, they are not close to each other. That is just an effect of perspective. When you see Jupiter and Saturn aligned, Saturn is still a lot further away from Jupiter. They're not right next to each other, but they will look like they're close to each other in the sky. So this is what makes, this is why we see planets seem to align sometimes in our sky. Since we can calculate very precisely the position of planets thanks to the laws of Kepler, and even before Kepler was there, thanks to Newtonian dynamics, in Newtonian physics, we can calculate the positions of planets, so we can predict in advance when planets will be aligning. I don't have any numbers or dates to give you here because I didn't research that just before. Sorry about that, but we can predict that. There is no surprise when planets align, and yes, so that is just an effect of perspective indeed. All right. So Hadrian, come to take a poem. Would like to take photos through the telescope. Do we need to bring our own T adapter? Anything else we need to bring? Oh, Rod. We do not offer at the moment any astrophotography. We are working on it. That's something that we would love to be doing. So we do that a lot. Luca here and myself are keen astrophotographers, as well as many of the other guides. If you follow the last live, Daniel was speaking to us. He's a very keen astrophotographer as well. So we love astrophotography. At the moment, it's not part of our regular offering, so you won't find an astrophotography dedicated tour. That said, we are always super happy to take, to organize bespoke experiences. So if you flick us an email, info@darkskyproject.co.nz. Tell us that you would be interested in doing an astrophotography tour, and we'll be more than happy to see if we can organize this. And now to answer your question precisely, we do happen to have T adapters for Nikon and Canon, depending on the camera that you have. You may, if you don't have a Canon or a Nikon, you will need to bring your own adapters. We also have a Metabones adapter somewhere to plug a Sony camera on a Canon T-ring as well. If you have any other brand, it will be a bit more challenging. But we have the equipment needed to do this with Canon, Nikon, and Sony. And so these questions reminds me of how much we love doing astrophotography and how much we would love to organize something like this. We are working on it, I swear. They are, yeah, you should be receiving an answer here if you with the email address if you want to organize this. All right. So we're going to be speaking with Dr. Ridden about the death of stars. But before this, I would like to give a bit of introduction on to just give a few tools, a few keys to try and understand a bit better what happens when stars die, what a supernova is, and these kind of things. And so I'll have to try and understand exactly what a star really is. Oh, so Sadaf Nagbi asking about celestial events like meteor showers. I don't have that at the top of my head. What are the next meteor showers? I'll have my colleague Luca working on this, and we'll give you an answer soon. To give you a date for next meteor shower. We will write that down in the comments. Oh, I forgot to talk about something important as well. We're in September. September, the 21st of September, something quite important is going to happen. I mean, something quite important. We are very used to it. It happens every year. That is the equinox. What is the equinox? You may have heard about solstice and equinox. What are those terms? Let me try and explain with this software that should make things quite easy to understand. So, in order to understand what a solstice or an equinox is, it's a very Earth-based thing. So let's go back to the Earth. All right, and I'm gonna move first to explain the phenomenon to a time that corresponds to a solstice and not an equinox. So let's start with the solstice, 21st of June. All right, 21st of June is the solstice, the winter solstice in the southern hemisphere, the summer solstice in the northern hemisphere. Let's see how that works. So I'm looking at the Earth here, and I'm gonna be looking at the Earth at what we call with the Terminator Line on the Earth. What's happening here? Why am I? Oh, yeah, I'm sorry. Ooh, that was a bit too fast. All right, so we are I've moved time a little bit, so we're no longer at the solstice, but close enough. And I'm looking here at what we call the Terminator Line. That's a very cool name for a line. The Terminator Line is the line that divides day and night. So see, it's passing right through here. On the left of this line is daytime. On the right of this line is nighttime. And during the equinox, you can see that this line is not north-south. It is from northeast to southwest. This means that the sun, in this configuration here, the sun is not above the equator. The sun is above the northern tropic, the Tropic of Cancer. And this means that the sun is actually coming, so the light of the sun is coming perpendicularly from this direction here. So the northern hemisphere gets more sunlight than the southern hemisphere. This is what makes seasons. When we are in this configuration, that is the summer solstice in the north, the winter solstice in the south, the 21st of June, in this configuration, we have longer days in the northern hemisphere, shorter days in the southern hemisphere, warmer temperatures up there, colder temperatures down here. This is what makes seasons. If I look at the other equinox, sorry, the other solstice, so it's not going to be the 21st of June, let's go back, but the 21st of December, exactly 6 months opposite. And let's look again at this Terminator Line. And there it is. And now we are in a more familiar place of the Earth. So the Terminator Line, as you can see, this time is going from northeast to southwest. So this time here, the southern hemisphere is receiving more light than the northern hemisphere. The sun is not directly above the equator, but it is down there, directly above the Tropic of Capricorn, the southern tropic. And therefore, the southern hemisphere receives more light than the northern hemisphere. It is summer down there, it is winter up there. And this is the 21st of December. All right, now equinox. Well, an equinox is the halfway point. The equinox is when, and I'll show you this, let's see our coming equinox. I'm going to put the exact date of the 21st of September 2021. And in the 21st of September 2021, we should see, so we are above India here, and you should see that the Terminator line, that line divided day and night, is pretty much exactly north-south. So the sun is pretty much exactly above the equator. So the northern and the southern hemisphere receive the same amount of light. This is when it's not summer up there or winter down there, it is spring and fall seasons. It is the shoulder seasons. It is when both hemispheres receive the same amount of light. That is what an equinox is, and we are getting close to the 21st of September. We are getting close to one of those equinoxes. All right, get rid of this. So, do you have any burning questions now?
Not at the moment.
All right. Yeah. All right. So let's move on to. You can continue asking questions, especially if you have any question for our upcoming interview with Dr. Ryan about how stars die, what is a supernova, are we in danger? No, I don't think we are. But let's Dr. Ryan confirm this. Let's try and explain what stars really are. In order to understand how they die, well, we have to understand what they are and how they were born in the first place. And for this, I'm going to move on to not a software this time, but a couple of images that should help us understanding this. So not this one here. Let's have a look at this one. All right. This is the beautiful Eta Carinae Nebula in a picture that was taken by myself. I'm proud of this one. I like it. We see here a big cloud of gas. That light. Well, you see plenty of stars in here, but all that gaseous thing. Let's zoom in on that gaseous region there. This is gas, plenty of gas, mostly hydrogen and helium and traces of other stuff, and many stars embedded in that gas. But that is gas, and that is very important. That gas is exactly what stars are made of. Stars are enormous, very dense clouds of no longer gas, but that was made of hydrogen and helium. So we have the same material here. This is what makes stars that we're seeing here. And in the shape of clouds. So what happens is gravity. Gravity will take part of those clouds and make them collapse under their own weight. Something that I say sometimes during my tours, I like to describe gravity as an evil force in space. Gravity tries to crush down everything. Gravity is constantly trying to push down those clouds and trying to make them as small and dense as possible. And then as the cloud of gas collapses under its own weight, gets denser and denser, well, eventually it will become hotter and hotter as well. And once this cloud of very dense hydrogen reaches a temperature of around 10 million degrees, something great happens: nuclear fusion reactions. So imagine, gravity continues wanting hard to crush that cloud as hard as possible, as close as possible. But these new fusion reactions happening in the center of that cloud will actually generate a lot of heat, a lot of pressure outwards. So the star is now in a fine balance. Gravity still really desperately wants to crush it, but whatever's happening inside of the star is pushing the other way. The star is in balance between those two forces. This is what a star is. We call that hydrostatic equilibrium. The star is in a, not perfect, but in a balance between those two forces. In order to maintain that balance, you need to continue doing those reactions, those nuclear fusion reactions in the core. And those nuclear fusion reactions require require light elements to fuse. The way it works is that two atoms of hydrogen, two nucleus of hydrogen, very, very tiny, the simplest possible nucleus that you can find in the universe, one proton each, that's simple. Those two nucleus of hydrogen will bump into each other and fuse together, and that will give you a nucleus of helium. This reaction, this fusion reaction, generates a lot of energy, but you need hydrogen. And eventually one day you will have no more hydrogen, just plenty of helium. This is what happens. This is why stars eventually die, because they run out of light elements to fuse. So a bit of a disclaimer here. It's not as simple as two nucleus of hydrogen making one nucleus of helium. There is several other steps in between, including some radioactive disintegration. I won't go into details, but this is a little bit more complex than that, but that is the idea. And the other disclaimer as well is that once the core of your star has no more hydrogen, but is only made of helium, it can still fuse. It can still fuse the helium. and it will fuse the helium and create heavier elements, carbon and oxygen. And eventually one day, once the core is filled with carbon and oxygen, it will fuse again and make heavier elements, etc., etc. Stars create everything step by step. They start with hydrogen into helium, then helium into oxygen and carbon, etc., etc. So step by step, they create heavier and heavier elements. The bigger the star is, the bigger the elements it can make. But there is one hard limit, and that is iron. Iron is an incredibly stable element. You can try as hard as you can to fuse iron, and you're gonna struggle. In order to fuse your iron, you're gonna need to pour more energy in than what you will get out of the reaction. So when the star reaches that, it's not a very good news for it, and Dr. Readen will talk about that in a few minutes. This is how you get supernova explosions. And this is how massive stars die. All right, just to give you a bit of context, this beautiful Eta Carinae Nebula here, I can try and show you where it is in the sky because I have it here. It is also pretty well drawn here on the stellarium. And actually, if you have a very dark sky, you can see it with the naked eye. Can you see that kind of pink patch here below the Southern Cross? The two pointer stars, Mahutoka, and below it. So the Southern Cross is pretty much halfway through the pointer stars and Eta Carinae. So this here is the Eta Carinae Nebula. So we can see that here. But honestly, my picture is much better. Come on. No?
Yes, Adrien.
Thank you. And in this picture is quite interesting as well because you can see several different levels of how advanced the process of collapsing cloud is. So here you have a bit of tenuous cloud in this direction here, but if you look at those tiny denser regions here, so these tiny denser regions, so I'm zooming in, so I'm losing a bit of resolution here because it's hard to zoom in, and please you can see here that my image is a bit out of focus, so don't judge me. But this here is a more advanced stage of cloud collapsing. So this here is getting hotter and denser, and we will have stars forming in there. Maybe there is already a star formed in there. And at the very last stage, before the star really shines through its shrouded cloud of gas, we get what we call a Bok globule, which is a very, very dense little patch of darker cloud here. What did I use to shoot this picture? Yeah, what did I use to shoot this picture? So this picture here was shot with an RC8 telescope, a Richley Chrétien 8-inch telescope, and the camera that I used here were the 5D Mark II, Canon 5D Mark II, astro modified. So the picture, the filter was removed. Helping me getting a bit more details on infrared lights, especially. You may have heard in the previous live that Daniel, or astrophotographer, uses H-alpha filters as well to capture that very specific light coming from the ionized hydrogen. I do not have an H-alpha filter. I did not use this. And you can see the signature of a Richley Chrétien telescope. So those crosses that you see around stars, they correspond to the cross that is on top of your telescope. This is the cross, the metallic cross that is holding the secondary mirror of the telescope. So when you see crosses like this on an image, it is very likely taken with the RC telescope, with the Richley Chrétien telescope. And by the way, this here is the mighty Eta Carinae. This beautiful cross here, this brighter star in the image, is Eta Carinae. That star, maybe may discuss this with Dr. Readen a bit later on, but that star may be one of our best chances to see a next supernova with the naked eye. That would be in a few thousand years, very likely, if it happens. But I still hope every single day. I look at the night sky and hope, did it blow up already? I would love to see that in my lifetime. But to increase my chances, I will have to live thousands of years, and that's not going to happen. But yeah, this is the mighty Eta Carinae. All right, so this is a nebula. This is a cloud of gas. This is how stars are born. Now, stars themselves, they're not all the same. And actually, even in this image here, oh, sorry about this. Even in this image here, what happens? I just broke that. There you go. That's the one. In this image here, you can see plenty of different colors in the stars as well. You see red ones, here, like here, Eta Carinae itself, and you see also whitish stars here, 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 blue stars, and there's different colors, and that gives you an indication on their surface temperatures. And actually, we can see that pretty easily on Stellarium as well. Let's have a look at a very famous red star. For that, we can go to Antares or Rehua. I know I'm talking about that star a lot because we love it, of course. There it is. Rehua Antares is a red supergiant star. It is very reddish. You can see the red color compared to the rest around. It is slightly colder on its surface. It is still hot. It's a star, so we're talking about thousands of degrees, probably between 3 and 4,000 degrees on the surface, something like this. And it's very bright because it is big. It's a red giant. Without going too much into details, before they die, stars swell, become extremely large, and the energy inside had a much larger surface to heat, so the surface will cool down, and this is why stars become red. Antares was not always a red star. It was very likely a bright blue star before that, but now it is in its red giant phase, so it has swollen to extremely large proportions, and it has reddened because the surface is a bit colder. By the way, it's when I say huge proportions, I'm not kidding. If we replace the Sun with Antares, Jupiter would be inside of it. That's how big it is. To understand that, let's put things into perspective by having a look here. Let's go back to our Sun. All right. So see, just in terms of proportions here, that's the size of the Sun. That's the orbit of Jupiter. We believe that Antares is that big. Again, Sun can get in the red giant phase. Red giant is an understatement. The word giant is an understatement. Really, red giants are huge. All right. So before moving on to our next step, just a quick question that we got from Bryce Curran. Can you explain about astro-modified camera? So yes, sorry, I've been just throwing that term without explaining what it is. On a DSLR camera, these cameras are mostly made to look at this, to take pictures during daytime. And during daytime, there is a lot of infrared light that is not very, very good, and you want to get rid of it to take nice pictures. So every DSLR camera, as far as I know, they have a filter in front of the sensor that blocks the infrared light, and to avoid that infrared light polluting your image. This is great for daytime images. This is not great at all for nighttime images. I want infrared light. You know, that's H alpha band, the light of the ionized hydrogen, happens to be in the infrared. I want to catch that. So I need to remove the filter in front of it. I did not do that myself because it's a very, very big job. I mean, big job, it's a precise job, and I'm not very good and steady with my hands. I paid a company to do this. So there are some companies around where you can send your camera, they remove the filter, and they send it back to you. So this is what I mean by astro-modified camera. The filter was removed to make it what we call a full spectrum camera. So there is no more filter in front of the sensor, and the sensor catches all the light that it can. And we do not block the infrared light anymore. So I've mentioned Antares when I was talking about red stars. Now we also have blue stars, white stars. So as I said, these colors are mostly due to their surface temperatures. And I like to go to a famous one that is going to be below the horizon, but I'm going to cheat a little bit here. Let's go to Sirius. Sirius is a hot star. It's a close one to us, but it's a pretty hot star. And it is way more white blue. It is hotter on its surface. It is less massive, a lot less massive than Antares, but Antares is at the end of its life. Essentially, the bigger, the more massive a star is, yeah, that's important. When you talk about stars, you don't say big and small. You say massive or light. The mass of the star, how heavy it is, that is what's important. So Sirius is more massive than the Sun, and therefore Sirius is hotter on its surface. And therefore it is whiter, bluer than the Sun. So Sirius is one of those hot stars. So you see, you have different types of stars. Small ones, big ones, you even have red giants. Let's see if I can see Proxima Centauri. I'm not too sure about that one. I'm not too sure about how this one will look in there. Oh, Sam. Thank you so much, Sam. Oh, I see that they put a love on the thing. Hi, Sam. So I saw that Sam Lord just commented in here.
Hi, Sam.
Hi, Sam. Sam, we
Hello,
miss you a
Sam.
lot. So Sam, well, she used to be a guide working for us. She used to be the team leader of the English team, and now she is in the UK where she's working for the Jodrell Bank Observatory, so a big radio telescope where she is working in. Science communication, working mostly with kids. And she told me that one of her first job was to board moon rocks. That's cool. So hi Sam, super happy to have to see you in there. All right, so Proxima Centauri. There you go. You can see it's a very tiny star. Don't expect to see that with your naked eye. It is the closest star to us, and yet it is not visible to the naked eye because Proxima Centauri is one of those red dwarfs. A red dwarf is a tiny star, not massive at all, very, very light, and therefore not very hot, and therefore not very white, and pretty red. So that's what you see in here. Proxima Centauri is one of those red dwarfs. However, whenever you see a red star with your naked eye in the sky, it's not a red dwarf, it's a red giant. So it's a normal, a bigger star that is towards the end of its life. Although red dwarfs make up around 75% of the stars in our universe, or at least in our galaxy, as far as we can tell, none of them is visible to the naked eye because they are incredibly dim. This includes Proxima Centauri, the actual closest star to us that is not at all visible to the naked eye because it is extremely, extremely dim. Now, when they come out of the star forming region, so where stars are born. So going back here to my Eta Carinae Nebula image. When the star gets out of this, I mean, once all the gas has been used to create stars, well, there's no more gas left. There's plenty of young stars, and you have plenty of different situations here. Stars, they start their life in clusters, open clusters, so they're close to each other, and then they slowly separate. And then some of them leave that cluster. So the stars, some of them are born alone, and many of them, the majority of them, are actually born in multiple star systems. And I'm going to just show you one of those multiple star systems before we call our professor, Dr. Ridden. And let's have a look at a pretty famous one. Actually, let's have a look at Sirius. We just saw Sirius. So Sirius, it is the brightest star in the entire night sky. It is the color of the dog. So here you can see this is what we call Canis Major, the large dog. And let's move on and let's zoom in. Let's travel to Sirius and ta-da, 2 stars. It's a binary system. Let's accelerate time massively so that we can see those 2 stars moving. And there you go. This is the motion they do. That is what we call a binary star. Most stars that you can see with your naked eye are binary stars. Take the Southern Cross. You see 4 stars in your Southern Cross, unless you're an Australian and you see 5 stars. For Kiwis, most of those 4, as far as I know, don't quote me on that, but at least 3 of them are binaries, and maybe 4, but at least 3 of them are binary stars. So you see 4 dots, but actually they are nearly all multiple star systems. I don't know about the 5th Australian star, so sorry, Aussies, I don't have this information. But we'll get there.
Sorry.
And Chris Murphy is saying that I have something in my teeth. Thank you, Chris. Love you. We miss you so much. Chris and Sam coming to crash our Facebook Live. I'm self-conscious now, and I cannot really. Okay, I'll check like this. So we will be talking quite shortly with Dr. Ryan Readen, but among the stuff that we're going to be speaking about, when you talk about supernovae, a topic that sometimes comes in as well is black holes. And I cannot really show you a black hole, but sort of. I'll show you a very special one, not the type of black holes that come from cataclysmic events, because I don't have any of those to show you in this software. But I'm going to try and show you the supermassive black hole we have in the center of our galaxy, which is called Sagittarius A star. Star as in the star. It's not a star though, it's a black hole. But there you go. So let's warp speed and get closer to that black hole, and here we go. I'll show you one thing that I find super interesting. By looking at the center of our galaxy, and keep in mind that we are looking at the exact center of our galaxy here. There are many more stars around, but the software only for logical reasons only shows a fraction of them. If I accelerate time a lot, we can see that those stars seem to be orbiting around something in the center that we don't see. There is nothing there in the center. And I'm sorry, Rod. I know that's not fair on you, Osis. I will try my best to get this information for next time. I'm really sorry. And to be fair, it's not fair to Aussies, Papua New Guineans, Samoan, and Brazilians. Among all the countries that have the Southern Cross on their flags, only New Zealand uses 4 stars. All the other countries use the fifth one, and that is not visible in the Kiwi flag. All right, so let's so you see here all those stars moving around a central object. They're moving very fast, so this must be a very massive object. That's a black hole. We don't see it. We see its gravitational effect. All right. Well, now let's try and understand all of this a bit better. Not just black holes, but also how stars, how they die, with Dr. Ryan Readen.
All right.
All right, kia ora. Kia ora, Ryan.
Hello.
Can you hear me?
Hey, thanks for having me.
Yeah, thank you for joining us. That's a real pleasure. Just a very brief word of introduction. So you are an astrophysicist that's working at the University of Canterbury's Research School of Physical and Chemical Sciences. So far, I'm right?
Yep, you're right so far.
All right, that's a good start. Also, I'm very, very happy to see that we are sharing a lot more and more with the University of Canterbury. So thanks to you, Ryan. Thanks to Michelle Bannister as well. Yeah, just a big thank you to all the scientist team, the scientific team, and the general everybody at University of Canterbury to allow that to happen. We're very happy to have you here. So you are specialist in exploding, like in very explosive events.
Yep.
This sounds super cool. First, I have to say, indeed, but also there seems to be plenty of different things in there. What is an exploding event? How many different types of exploding events? What can you tell us a bit more on what type of events we're talking about?
Yeah, so it's a really interesting and dynamic field to be part of. So I'm very happy to have worked on it so far. And as for the variety of exploding things, there's a surprisingly large variety of exploding things. So there's the perhaps more standard thing that people are familiar with, the supernova, where you have a massive star that itself up in an enormous explosion. But then you can have other fun things like a gamma ray burst, where a kind of the death of a star is concentrated in a beam of energy, and you better hope you're not within the line of sight of that beam. And then you can have other things called kilonova, which generally involve massive objects slamming together. We've observed a few of those in recent years, which have been very interesting and very insightful for different aspects of the evolution of the universe. And what other exploding things are there? Just in general, stars can sometimes get quite unhappy with the way that they are and want to throw off some external material, so they'll erupt in great flares and things like that.
Yeah,
so you'll find, if you look at the sky for long enough, you'll find that there's a whole lot of stuff going on, a whole lot of things that are changing.
And speaking about what you just mentioned, that sometimes stars, not when they die, but sometimes they do have exploding flares. This is what happened to Eta Carinae. So I've been talking a bit earlier about Eta Carinae, the nebula and the star inside this nebula. And from what I understand, about 100 years ago, this star became very bright suddenly. What happened?
That's an ongoing question because it's quite strange. Because usually when you have a massive star like Eta Carinae, when they blow up, and then they're gone, and they don't exist anymore. But for Eta Carinae, it's persisted since the time that it apparently blew up. So this has led to quite a mystery, trying to solve why Eta Carinae is still there. And one way that my research group has worked on this is that they've looked at light being bounced off sheets of dust floating around in space. So the light traveled from Eta Carinae, bounced off this sheet of dust, and traveled to us here on Earth. And that time delay of it going to the sheet of dust and then bouncing to us was used so that we could see events that happened hundreds of years ago. And I think one of the leading ideas at the moment is what happened is perhaps it was a triple star system, and that one of the stars ended up kind of colliding and ramming into the main star, causing such an enormous outburst of material. But I think this is still speculation. We don't have solid evidence on this at the moment. But it would be certainly an awesome explanation for why it did what it did, because not often you get to see stars colliding.
Let me try to understand. So what you're mentioning about light reflecting on the, so we get the straight line of sight from Eta Carinae, and that takes around 7,500 years for the light to reach us, because it's 7,500 light years away. And so are you saying that you can look at light that has gone another way and then bounced towards us and therefore took a longer time? Is that what we can see?
Yeah.
Oh, that's very interesting. That's like
exactly
an echo.
right.
That's an echo.
Yeah.
Ah.
So it's like an echo, or like big mirrors suspended in space. The light bounces off and comes back like an echo would. And it is very powerful, and you can see it in images if you have a powerful enough telescope. If you take images, say a couple months apart, you'll see kind of this front of light move through your images. So that's the profile of light that you want to look at for the light echo. And there's super interesting things.
Yeah, that is fascinating. Well, okay, this is fascinating, but that's a bit complex. Let's get back to something that is still complex, but a bit more straightforward. So many stars, when they die off into a big explosion that we call a supernova. First, is that correct? So what exactly do we see when we see one of those stars blow up? The light that we see, what it is? What is it? What happens to it?
Yeah, that's a very good question. So, if you're a very big star, the end of your life will be quite dramatic. And the way that it's dramatic is that at the center of your star, it fuses atoms together to make iron. And then it can't fuse those iron atoms together anymore to make heavier atoms. So that causes the entire star to kind of give up and collapse on itself. And you get this rebound of material that comes out of the star, and lots of fusion that happens at that time. So fusing heavier and heavier atoms, harnessing the gravitational energy of a collapsing star, essentially. So once that happens, you can have some very interesting and radioactive compounds form. Quite often, the main source of light that we see from supernova is light that's being produced by the decay of radioactive atoms like nickel 56. So those decay, and they release light as they decay into cobalt, I think. And that brightness that we see from a supernova, it's just so bright that it overpowers pretty much everything around it. It's brighter than the galaxy that it was sitting in. And because it's so bright, we can see them so very far away from us. And by studying these supernovae, we can understand some pretty fundamental aspects of our universe just by watching how stars kind of collapse and die at the very end.
And then, from what I understand, I think that, so I'm showing you as you speak, we can see in the background a beautiful, very famous image taken by the Hubble Space Telescope of the Crab Nebula. So this is not exactly what you mentioned, but a little bit later. From what I understand, so they do evolve slowly over time, and we can see that evolution. If I remember well, the Crab Nebula was caused by a supernova about 1,000 years ago. Is that correct?
Yeah. So the material that's flying out of a supernova is traveling at like tens of thousands of kilometers per second, I think. They're traveling extremely quickly. So in the very early stages, it looks like it goes quite quickly. But even still, the Crab Nebula is expanding quite fast. And there's a few cool time lapses where over the course of a few decades, you can compare images of the Crab Nebula, and you can see that filamentary structure slowly shift outwards. So it's an awesome
It's quite
feature
obvious
to
here in
have
this image.
close by.
It's really really impressive. Just Karen, that was Karen in the comments mentioning how cool it is that everything, including us, comes from elements that burst out of exploding stars. So this brings me back to something that I like saying in my tour. So I know that it's a bit of a stretch, but can we say that every element that is heavier than iron was formed in something like this, in such an event? So if you have a golden ring around your finger, did that gold come from this type of event?
Pretty much, yeah. So iron is kind of the hard stopping point for stars making stuff through nuclear fusion as they live their lives. So anything past iron, you need a very energetic process to make. So for most, each one of the different ways that you can explode stars or slam them together can produce different aspects of the periodic table past iron. So a great discovery that was made in 2017 was the first kilonova that was caused by two neutron stars. And there's a neutron star sitting at the center of the Crab Nebula. If you have two of them and slam them together, what you actually end up making is a lot of stuff, and a lot of that stuff is gold. And we think that the majority of the gold in the universe was actually produced by neutron stars slamming together millions to billions of years ago. So each one of these heavy atom groups that we have their own kind of origin from the death of some extreme event happening.
All right, so that brings me to another question. Then you're been saying the word neutron star, and when I look at this image from the Crab Nebula, I kind of give the impression that the whole thing's gone. The stars exploded, and you can see the massive explosion. But you mentioned that there is a neutron star in there. What is this? So something is left over after a star dies, right?
Yeah, well, most of the time, yeah. So sometimes you could have the everything just goes wrong for the star and it just completely blows itself to bits, and we have no hope of finding any remnants, we call it, sitting at the center of where that star was. But quite often, if you have a massive star, as all of the material comes rushing down and collapsing onto the core of the star, it can cause something known as or rather, kind of like electron capture, but the electrons get forced into the protons and you make neutrons. So you end up with this very bizarre object that's about 30 kilometers across, and it's so dense and so strange that it's one of the heaviest items that you could find in the universe. And they often spin very quickly as well, because it's like how ice skaters, when they spin and pull their arms in, they spin faster. It's like you're compressing the spin of an entire star down to something that's a few kilometers across. So they can spin incredibly rapidly. And the ones that fire radio beams out and point towards the Earth are called pulsars. And at the center of the Crab Nebula is actually a pulsar that some people, if you're lucky enough to have really good eyes, can actually see. I haven't seen it myself. Very few people can actually spot the crab pulsar.
What, you get with your naked eye?
Yeah, this is pretty amazing. There
Wow.
was a few. There's a famous story from many decades ago where I think it was Wilson Observatory in the USA had an open day where a lady was looking at the Crab Nebula and saw regular flashes, and she notified the astronomer that was there with her. And the astronomer, of course, thought, "Oh, she doesn't know what she's talking about," and then sent her on her way. But if he believed her, then they would have found a pulsar before, or decades before, they were actually discovered through radio astronomy.
Yeah, right. This is that's quite impressive. I didn't know you could eventually see that to the naked eye.
You need really good eyesight,
Yeah,
though.
I wouldn't at all be able to see that with my naked eye. Definitely not. So now we're talking about those exploding stars, supernova events. Is this is it our fate? Is it the fate of our solar system? Are we going to be eventually destroyed this way as well? I believe no. Our sun is too small, right?
Yeah, so not all stars will explode. Stars that are 8 times more massive than our sun will explode. Stars that are less massive than that eight times the solar mass line will die through kind of a more gentle process where they'll grow into a red giant, and they'll grow so large that their gravity can't hold on to the outer layers of the star anymore. So those outer layers will just gently drift off into space and blown away by the solar winds until all you're left with is the very core of that star. And that core is known as a white dwarf, and it's mostly made out of carbon and oxygen. So it's the remains of a star like our sun. So stars around the size of our sun can only fuse atoms up until around carbon and oxygen. So they will never get close enough to the iron fusion process. You need to be very heavy to actually have the energy to fuse atoms into iron.
As you were speaking, I've just changed the image behind. Now you guys can see my image of the Crab Nebula. I won't leave that too long because it's nowhere as good as the Hubble image, of course. But just to give you an idea, that's what we can see. And for the record, through a telescope, you do not see that at all. It's I mean, you see a very very faint thing if you have a big enough telescope, but it's nowhere as good as this. So yeah, we're pretty safe. The sun will not die into a supernova. What about nearby supernovae? Is that something that can affect the Earth? Has this ever happened?
There have been a few stories I've seen every now and then that suggest that there are records of mass extinction events long in the past, which you could perhaps associate with a nearby supernova. But I don't think there's any concrete evidence to say that as of yet. But earlier this year, some astronomers and atomic physicists at the Australian National University, where I did my PhD, they found atoms at the bottom of the ocean which could have only have come from a supernova. And I forget exactly the timescales they were talking about, but the idea is that very long ago, a supernova blew up, its material expanded away, much like the Crab Nebula is doing now, and then sometime in the future, the sun and the solar system passed through the debris, and the Earth collected some of that, which settled on the surface, or settled on the floor of the ocean. So there are definitely supernova around us. As for the future, there are no stars at the moment that seem like they're going to blow up anytime soon, which is a relief for our safety, but also kind of a bummer for me, because I would like to have a nearby supernova, and I'm sure many other astronomers would as well, because the detail of understanding you'd be able to create for a nearby event would be much greater than ones that we're seeing millions of light years away from us.
All right. Well, then what about Sirius? So from what I understand, the dying star can be a supernova, but there's another type of exploding event that is when a white dwarf creates a lot of matter and reaches a certain limit, it can blow up as well.
Mm-hmm.
And Sirius is a system that has one of those white dwarfs and one of those other stars. So is this a potential danger here? Danger, maybe very long term, but is this something that could affect us? Because Sirius is pretty close.
Yeah, so the type of supernova that gets created from a white dwarf accreting material is called a type 1a supernova. That doesn't mean too much, I guess, but what it means is that the white dwarf blows up in some way. And those ones are rather energetic explosions. So you want to be far away from them. I'm not actually sure. I think it's something like 100 light years or something like that is the danger radius for supernova.
For reference, Sirius is 8 light years away.
So we might have a bit of an issue.
All right, but yeah, Sirius A, we would have to wait for Sirius A to be a bit older. We're nowhere there yet, so we should be fine. Don't I want not to alarm any of our viewers. But yes,
I've heard no astronomers talking about the risk of Sirius going supernova. So we're fine.
Right. So these events seem very energetic, very bright. What are my chances of seeing one with the naked eye, say, tonight?
Unfortunately, very low. So if a supernova went off in, let's say, somewhere in the arms of the Milky Way that we're in, we'd be able to see it quite easily. It would even get so bright as to rival the full moon if it was close enough. Oh. So you would cast shadows from an exploding star some tens to hundreds of light years away. We would also be able to see them in the small and large Magellanic Clouds, which are visible from the southern hemisphere. And you'd probably also be able to see, without too much effort, a supernova going off in the Andromeda Galaxy. But once you start to get further away, it gets harder and harder, of course, because light gets fainter with the inverse square of distance.
So as you were speaking, so you mentioned the Magellanic Cloud. So I'm now showing behind you. There's an image of that I took as well of the Tarantula Nebula. So this is an enormous star-forming region in which we've seen the last time a supernova was visible to the naked eye, if I'm not mistaken, was somewhere in there. Is that correct?
That's a very good question. Let me. I'm not too well versed on my recent supernova,
Yeah, no,
but
so from what I say, if I remember right, in 1987. So that was not that short time ago. I was 1 year old. But
oh, that is pretty close.
but he's apparently nowhere as bright as this. So I'm aware of this because we have some astrophotographers working for DASCA project that have been around
Oh, yeah.
for quite a while and did have like they have been doing pictures for quite a while and did take a few images of this back then. So that's I mean did witness this one back then.
Yeah, you're quite right. I've just looked it up now. There's a Type 2 supernova, so that's a core collapse supernova. So the opposite, or not the same as what could
Okay.
happen with Sirius.
All right.
That's cool.
What about black holes? So sometimes I tend to think that to feel like supernovae are in a way associated to black holes. Can it work that way?
Yeah, they certainly can work that way. So black holes are kind of tricky to make. You might not think it, they are. So there are a few different mechanisms that you can have. So the challenge with making a black hole through a supernova is if you're not careful, you're going to throw away most of your mass in the supernova, where you want to kind of cram it all close to the core so that it will pass a magical limit and crush itself down into a black hole. So another way it can happen is if the star just doesn't really have the right conditions to form a neutron star and cause all the material to bounce back out and make a supernova. It could just be that the core itself is just too heavy and it immediately collapses into a black hole. Then the rest of the star just kind of follows down. So that's what we call a direct collapse black hole. And I think there's been one or two that may have been observed where with Hubble you can observe nearby galaxies and you can take inventory of the stars that you can see between images. And if a star is suddenly gone, but you saw no supernova, then it's a good sign that you had a direct collapse black hole forming.
So yeah, we're talking about a massive star dying into a black hole with no visible supernova.
Yeah, or if it does have some kind of visible product, it's too fast for us to see with the technology we have currently. Another way is if you have something called a fullback supernova, or if the star kind of blows up in a funny way that doesn't eject the material properly, it can actually fall back down onto the neutron star. And the material raining down on the neutron star could push it over the limit and form a black hole as well. So there are a few different mechanisms for making black holes from supernova, which make them kind of tricky. And understanding how supernova explode and how they, or the remnants that they create, is a big ongoing study in astronomy, because each object is kind of weird in its own way, and trying to understand the global weirdness and build some kind of physical model for what happens is quite hard. So that requires the work of brilliant theorists and observational astronomers all over the world to gather the data and make sense of it all. So it is very much a great collaborative enterprise.
Back to our immediate skies so you may have heard about a lot of people have heard about Betelgeuse acting quite strangely lately, and there have been talks of Betelgeuse going supernova. So we have a question here from Karen: is Betelgeuse more likely to go supernova than Sirius? Are we in terms of timescales? In terms of is Betelgeuse gonna go supernova? Is it gonna happen today? Should I go in my bunker now?
So we'll be safe if it does blow up, but the likelihood that it will blow up is actually, unfortunately, quite low. So we thought that it was very close to the end of its lifetime, which is why astronomers got really excited. I think it was last year when it suddenly dimmed an awful lot, because we thought, oh, maybe this is it, right? Some strange process is happening on this star that we haven't seen before, and we know it's close to the end of its life. So maybe we're seeing how a star really starts the process of forming a core collapse supernova. But unfortunately for us, what ended up happening was that through processes at stars kind of get a little bit volatile and can throw out lots of stuff.
Okay.
And that stuff can coalesce and make clouds of dust and things like that. So what we think happened was that a cloud of dust orbiting around the star passed between us and the star and obscured some of the light. So it just kind of cast a shadow on us, which caused the brightness to dip. And as the dust cloud moved away again, the brightness went up to how it used to be. And there have been some studies since everyone got excited about Betelgeuse as to how long it might have left to live. And it's been revised from like any day now to like hundreds of thousands of years lifetime. So I don't think it's going to blow up anytime soon, which is unfortunate for me.
I like how you astronomers want things to blow up. Actually, you sound
Yeah, it's
excited at
fine
the
for us. We
idea
just get data.
of one of those massive explosions. So I just put in the background here to give a bit of context where Betelgeuse is. So if you guys want to have a look at Betelgeuse with your naked eye, you're not at the right time of the year, unfortunately. You'll have to wait for, it's more of a summer constellation, but the very famous and mighty Orion right here with Betelgeuse that from those southern latitudes will appear at the bottom right of Orion. It is actually one of the shoulders of the mighty hunter Orion that I can show it. I can show it like this. So we have another question here, and we're going to have to wrap it up pretty shortly. So that's going to be maybe one of the last ones here. But a question from Okinawa in Japan, asking a bit about magnetars. So these are two full questions. Is a magnetar one of those types of object that you can get after a supernova explosion? It is one of the possible remnants for a dead star. And also, can you make black holes by colliding two magnetars?
Yeah, both fantastic questions. So magnetars are real objects, which is fantastic to say because for a long time they were kind of theoretical. But we have observational evidence that show, or at least we think, that they exist. So how is a magnetar different from another object? So they are extremely magnetized neutron stars. So we don't really have a good understanding of how magnetism works for a lot of astronomical stuff, and the death of stars is no exception. But the idea is something along the lines of when the star dies, kind of the magnetic field gets baked into the neutron star and kind of compressed. So you end up with a very small, dense object with a very strong magnetic field, which is spinning extremely quickly. And because the magnetic field is so strong in spinning, it creates a very strong effect on its local environment. So there are some supernova that we see that are called superluminous supernova. And these ones are strange because they are so bright that our understanding of what powers supernova doesn't really explain how they got so bright. And a way to reconcile this is to say at the center of this supernova, you formed a magnetar. And the magnetar spinning and doing its stuff is accelerating particles faster and faster and throwing them away. So kind of providing an extra kick after the supernova actually happened to particles to make them expand faster and collide with other particles and cause a much brighter event. So magnetars are definitely really cool objects that we still know very little about because neutron stars themselves are very strange. We know extremely little about the actual structure of neutron stars. You can have exotic things like superfluids running around in the cores of pulsars and magnetars, but I don't know too much about that. And the question about colliding magnetars, you certainly could do that. I'm not sure exactly what kind of effect that would end up giving. You would produce a black hole at the end of it, like if you collided two neutron stars together. But no doubt it would become quite tricky and quite complicated with the magnetic fields in play, because those magnetic fields are extremely strong. Yeah, so they're very cool objects and something that we need to find more supernova and find more of their type of objects so we can try and understand them better.
All right. Well, we are getting to the end of our time together here. So I start by thank you so much, Ryan, for joining us here and for answering all those questions. I just want to finish on one thing. So I know that on the side of your on the side of your job as a researcher, as a doctor in astronomy, you also work quite a lot in public outreach, and you've been doing activities, public outreach activities with kids in Australia as well, which leads me to my question: do you explain supernova to 5-year-old kids, and how
Pretty
do you?
often.
What does that look like?
Yeah, kids really are excited to learn about how stars blow up. And in fact, in 2 weeks' time, I'm going to be giving a talk about black holes to an outreach group that I help run called Young Stars. So if either you want to learn more about black holes or you know some kids who are keen to learn about black holes, you can find the Young Stars program on Facebook. And it'd be great to have more Kiwis joining, because at the moment, I think we get more people from America joining us than from New Zealand. So that definitely,
All right.
hopefully, will change.
We'll definitely put links and things like this in the comments so that we can find that again. Well, Brian, thank you so much. I can tell you as well that I know that we're going to have us here, the guys at DASCA Project, a chance to meet you face to face or mask to mask. I know that we can't wait because we have plenty of very complicated questions. I received a list of questions from the guys to ask you, but I kept them not for now because they are actually a bit over the a bit complex, and we don't want to get too far into details. But we can't wait to meet you. Thank you again for participating. That was great, and we'll see you very soon.
Yeah, sounds good. Thank you again for having me. I'm always happy to answer questions.
It's perfect. Thank you so much. Have a great night, and and see you soon, Ryan.
Yeah, see ya.
All right. So thank you guys for joining us. Just I have one last question that was popping up. So Richeton, cœur avec les doigts. So we don't really bother naming stars. We don't discover new stars. Whenever astronomers do research, they don't really bother naming stars. There's, we believe, 400 billion of them in our own galaxy alone, and there will be a lot more in other galaxies. So it would be a waste of time to name them all, which is why we don't really bother. So the Greek, the letters that you're mentioning, the Greek letters that you're mentioning, is what we call the biodesignation. It goes with the Greek letter followed by the name of the constellation. So, for example, Alpha Centauri. Alpha is the first letter in the Greek alphabet. It means that it is the brightest constellation, the brightest star in the constellation Centaurus. Beta Centauri is the second brightest, etc. So Sirius, which is the brightest star in the constellation Canis Major, is also called Alpha Canis Major. That is what we call the biodesignation. But yeah, to be we already completely ran out of Greek letters, and that's fine. We don't need to name all of those stars. So thank you very much, everybody. Thank you for all the feedback. We love the questions. You can get your questions ready for the next time because we will be back. Thank you very much. Have a good have a good night. Stay home, stay safe. Hopefully not for too much longer. We don't know, but for now, let's stay home, stay safe. Kia kaha. Thank you very much, everybody, and we'll see you soon.
Thank you.
Thank you very much.
Bye.
Thank you.
See
Bye.
you next time.